This video is sponsored by PCBWay. Hello there and welcome back to another video. In today's video, I'm going to be building an upgraded version of the wireless temperature and humidity monitor system that I made a little over a year ago for my home lab setup. This sensor system consisted of a base station and a wireless sensor. The base station would sit on my desk, and the wireless sensor would live on my server rack in its closet, therefore allowing me to check on the ambient temperature in there without having to get up, go over to the closet, open it, and grab the little temperature sensor that I used to have sitting in there. For this purpose, this device worked great. However, it wasn't without its flaws and limitations, which mainly pertain to the base station. The base station has its own temperature sensor built into it, which is great because I wanted to measure the temperature at my desk. However, it always read several degrees Fahrenheit too high. And by several, I mean that it would actually be maybe mid-80s in here during the summer, and it would be spitting out 94 on its display, so nowhere close to accurate. After some careful brainstorming, I figured out what I believe to be the root cause, or really a couple causes, for the issue. First off, the sensor in the base station enclosure is not very well ventilated, making it far less sensitive to small ambient temperature changes. But further, and this is where the second issue comes in, it doesn't expel the small amount of heat created by the control electronics effectively. The remote sensors use a simple BME 280 sensor, Arduino Nano, and nRF24 inside them. The Arduino Nano produces an absolutely tiny amount of heat, meaning that even though the BME 280 is quite close to it, it doesn't throw off the measurement meaningfully. However, the base station is different, because not only does it have extra peripherals, namely the OLED display, but it also uses an ESP32 microcontroller for extra processing power, as well as Wi-Fi functionality for possible future Home Assistant integration. The issue is that the ESP32, while being a much more capable and powerful microcontroller than the ATmega32AP used on the Arduino Nano, it ends up drawing far more power and therefore generating much more heat than the Nano. And before I offend the ESP32 community, I am not saying that the ESP32 is inefficient or runs hot, it just runs a lot hotter than the Nano in a less ventilated enclosure with a temperature sensor right next to it. I took some videos of these two devices as well as their separate microcontrollers to demonstrate this, and here you can see the exact issue at hand quite clearly. Inside the base station, the ESP32 is getting a lot hotter than the Arduino Nano is in the remote sensor. Certain parts of the ESP32 module are even at about 32 degrees Celsius, and this is with the lid of the box off. The proximity of the temperature sensor to this heat and the subpar ventilation of the enclosure is almost certainly the reason that the temperature reading of this sensor is so off. When looking at the Arduino Nano, you can see that the only meaningful heat coming off of it is a tiny bit of heat coming from the microcontroller's core, and even then, it's running nowhere close to as warm as the ESP is. So yeah, some pretty notable design changes are going to be required here, mainly to the base station. However, while I'm at it, it might be worthwhile to redesign the remote sensor to make it easier to assemble and to improve its thermal design, even though I don't think that it's really suffering from too major an issue with that. Plus, wouldn't it be cool if, as an option for the remote sensor, you could build one that has a screen on it that displays its own temperature locally. So if you're in another location, you can check the sensor's readout without going all the way back to the base station. So I think I'll redesign the basic remote sensor using exactly the same components, a BME 280 temperature sensor, nRF24 radio module, Arduino Nano, and USB-C port for power, but I'll absolutely be redoing the PCB and enclosure. Then I'll design another PCB and enclosure for a second kind of remote sensor, one that's identical to the regular one, apart from the fact that it also has a small 1-inch OLED screen on it, which will display its own temperature and humidity readouts, so that if it's, say, in your garage and the base station is in your office, you can still check the temperature of your garage from the garage using the sensor without having to go to your office to see the readout or using a different temperature humidity sensor with its own screen on it. Then for the base station, I'll keep the same base components because I think they work well, and those being of course the BME 280 sensor again, nRF24 radio, and ESP32 microcontroller. I like the ESP32 for this application mainly because of the fact that it has Wi-Fi functionality, which, while I'm not that interested in smart home stuff and therefore don't do it, I know some people will adore the fact that with some additional programming, the base station of this build is ready for integration into Home Assistant. There are only two major changes to the base station's electronics hardware, and those are that I'm going to be using a much bigger OLED screen, because the tiny 0.96-inch ones, while great for a lot of things, aren't the best choice for this application. I don't have the larger one at the time of filming this clip, but you'll see it soon, and it's pretty awesome. Then, the second change that I'll be making is that compared to the keyboard switches I used as buttons in the original build, I'll be upgrading to some proper metal panel mount push buttons, exactly like the ones that I used on my recent motorized fader PC volume mixer project. And with those parameters in mind, I set out to design the new PCBs and enclosures for this project, which will have much more care put into their ease of assembly, thermal design, and overall form. Starting with the least interesting of the modules, the wireless sensors. The regular sensor box is very similar to the original one, apart from the fact that the USB-C port is mounted to the lid, making it easy to screw onto its mounts and then put into place. So now you don't have to fight for your life to screw the screws into the 3D print with an Allen key at a 90-degree angle. There is one more major difference as well though, and that is how separate the temperature sensor is from the rest of the electronics. There's a thick dividing wall between the rest of the electronics and the temperature sensor, and the PCB just sneaks under it to place the temperature sensor in its own thermal chamber. Additionally, the ventilation of this chamber has been done differently, with two large holes in the PCB in combination with vents on the top, side, and bottom, all of which should allow for natural convection to occur very easily in this chamber, therefore keeping the temperature readout accurate. As for the remote sensor box that has a screen on it, it's identical to the regular sensor box, other than that it's a bit taller and it has a cutout in the side for a screen. And that's the majority of the changes with this module done. Of course, it assembles in a different order and is actually a 3-piece enclosure as opposed to a 2-piece one, but I think that we can move on to the more interesting one now, that being the base station. This design shares some very similar concepts with the two remote sensors, including how the temperature sensor is placed in a separate thermal chamber with ample ventilation that's been designed with natural convection in mind. However, the rest of the design is fairly different, as it should be, because this is the main hub that gets interacted with and therefore serves a very different purpose. First off, I changed the angle of the front panel so that it's a little bit more friendly to look down at, as you likely will be, whether you're sitting or standing. Additionally, it's built to accommodate the nicer panel mount buttons and larger 128 by 128 1.5-inch OLED screen that I found for it. Also, this enclosure is designed to be a lot easier to assemble because instead of having to solder and heat shrink wires inside of a tiny box to assemble it, this one allows you to do all the hard work on the front panel while it's completely detached and open to work on. And then you can mount the front panel, plug in the 2 headers of cables, and that's it. So with that, I think it's time to get these parts manufactured and assembled, and that's where the sponsor of today's video comes in, PCBWay. PCBWay is a company that offers high-quality manufacturing services, 3 of which are very relevant to this project. Those 3 services are their PCB manufacturing service, 3D printing service, and CNC machining service. They offer a myriad of different materials for 3D printing and CNC machining, as well as several surface finishes, so that any part you ever need should be no problem for them. Plus, they have a ton of different options for your PCBs too, including a bunch of useful colors among a whole ton of other things. For this project, I ordered 3 different PCB designs and I got them in red, blue, and yellow solder masks, which I think makes them look amazing. Plus, it allows me to easily differentiate between some of the similar looking boards with just a quick glance. Then, I also had the front panel of the base station CNC machined, and I think it came out amazing with a bead blast and anodized gray finish. As for the 3D printed parts, I printed them myself, but if you don't have a 3D printer, PCBWay can do that for you too, and has a ton of different processes and materials available. Check PCBWay and their services out at the link in the video description, and thank you again to them for sponsoring this video. Now, let's get to work building this project, but before I get to soldering all the PCBs together, I would like to address the elephant in the room, the CNC machined front panel. Some of you are probably wondering why on earth I designed this build to be so overkill and so much more expensive than it would be if I had just made the front panel 3D printed. And to that, I say, I didn't. The front panel is designed to be completely 3D printable, and I 100% understand that that's what most people choosing to actually build this project will do. I just happened to get the CNC machining service for free because I'm sponsored by PCBWay. I think it's an awesome service that can add a lot to a project, and because this part is also quite easily CNC machinable, I chose to get it machined because, come on, it looks so cool. In any case, I assembled all 3 PCBs. However, I actually made a couple of mistakes while doing this, which I'll address now so that if you're following along, you don't make them as well. Generally, I like to place my microcontrollers in female pin header sockets so that I can easily pull them out to program them out of circuit or to reuse them in other projects when I'm done with one. However, in this design, due to the compactness of the base station, the added height from putting the ESP32 in a socket will actually cause it to interfere with the backs of the panel mount push buttons on the front panel, so make sure you solder your ESP32 directly to the PCB. Moving on to the next mistake that I made, which is actually also socket based, I chose to put the nRF24 modules in sockets as well, but this actually turned out to be a problem. For some reason, the added resistance of the connections in the socket caused the nRF24 to have issues with successfully transmitting data when being run at its maximum transmit power, which is what they're all set to maximize their range within a house. So also solder the nRF24 modules directly to the PCB, as this will avoid that issue. But now, with all of the PCBs soldered up, let's work on assembling each of the 3 modules after you first upload the code to each of the microcontrollers. The programming USB ports are not easily accessible once the modules are closed, so don't forget this or your wrist might get a little sore from having to unscrew and rescrew a whole bunch of stuff. Starting with the basic remote sensor, the first step is to use a small jumper to bridge 2 pins on the PCB that will select which address the sensor transmits on. Address number 1, which will cause the sensor to report to the base station as remote sensor 1, is closest to the Arduino, and address 5 is the furthest. The second step for this assembly is to attach some wires to the power input connections on the PCB. They should be marked with a positive and negative in the silk screen of the board, and I would recommend leaving these wires at least a few inches long, as if you don't, assembling the lid with the USB port will kind of suck. Once those wires are on the board though, you can take the bottom panel and screw it onto the main body with the board sandwiched in the joint between the two. I recommend partially screwing in the M3x12 screws to the bottom cover, just enough so that they slightly stick out the other side of it. These small pegs will then hold the PCB in perfect alignment while you place the middle part of the chassis over it and screw everything together. Next, let's mount the USB-C port to the lid, which can be done with 2 M3x6 screws and possibly some washers between the PCB and the lid if the USB port doesn't quite sit at the right height. Then solder the positive power input wire to V-bus on the breakout board and the negative power input wire to ground on the breakout. With that, you can screw the lid on with 4 M3x8 screws and voila, the basic temperature sensor is complete. So now, let's move on to the other kind of wireless temperature sensor, that one being the one with the screen. For this one, the only difference is the addition of the screen, which I recommend that you do right at the start. Otherwise, it could be kind of challenging to screw the M2 nuts on. But before you screw the screen into place, I recommend soldering 4 DuPont wires to it with female ends, which will allow you to connect it to the PCB. Then, the screen can be mounted with 4 M2 screws and nuts, and the length of the screws is actually quite dependent on whether or not you put the Arduino in a socket. If you didn't socket the Arduino, basically any length of M2 screw will work to mount the screen for all 4 of the screws, and slightly longer ones, like M2x8s, will make it easier to get the nuts on. However, if you socketed the Arduino, the bottom 2 screws have to be M2x4 screws in order to clear the USB port. Then, the rest of this assembly is practically identical to the other one. Place the address jumper, solder wires to the PCB for power input, mount the PCB to the chassis with the bottom lid, mount the USB port to the lid, solder the power leads to the USB port, and then right before you close it, the only different step is to make sure that you have the OLED plugged into the PCB. And with that, you're done. So finally, it's time to work on the base station. And as much as it seems like the base station might be a harder build, it really shouldn't be. The first step that I recommend with the base station is to solder 2 relatively long leads to the V-bus and ground connections on the USB breakout, and then to thread those 2 leads through the small hole in the thermal isolation wall between the electronics chamber and the temperature sensor chamber. Then place the USB port in its spot and hot glue it into place, because it wasn't really possible to get usable screw holes in here. Then connect the 2 power leads to the PCB and mount it into the chassis with the bottom cover, just like on the other modules. And now we can move on to the front panel. Mounting the push buttons to the front panel isn't hard. The only thing you need to note is that you should make sure that all their contacts aren't facing vertically and are instead all horizontal, so that the risk of them interfering physically with the ESP board is lower. Then connect one contact of all 3 buttons together and solder a DuPont wire to this shared connection. The other contact on each of the 3 buttons can then connect to its own DuPont wire with a female end, so you should have a total of 4 female DuPont connectors for the buttons. Also, I do recommend using some heat shrink here. I chose to be lazy and not use it because due to the design of the chassis, these connections shouldn't really be able to touch anything bad, but it might be worthwhile. Then the OLED screen can be mounted to the front panel with some M2 screws and nuts, and the length of these screws doesn't really matter, but I used M2x8s. Oh, and you should do the same quad DuPont wire thing to this OLED that you did with the one in the remote sensor that has the screen, preferably before you mount it. Otherwise, it might be a little more challenging. Then you can plug the front panel connections into their corresponding headers and close the front panel up with 4 M3x12 countersunk screws. And so, with that, all of the modules are complete. Of course, if you're building multiple of one or both kinds of remote sensors, go and do that, but make sure you select different addresses for each sensor with the jumper, and make sure there are no more than 5 total sensors, as this system is only built to work with 5 or fewer remote sensors. Also, as a quick note, if you're building this system and using it with fewer than 5 sensors, there's a spot in the code to block sensors from showing up while paging through the menus, because the header that I put on the PCB to do this in the base station doesn't work quite right. And so, at this point, all of the modules should power up and start working seamlessly. So let me run through the basic functions that I built into this system, which I'm honestly incredibly pleased with, because I was finally able to implement all of the features that I wanted to in my original version, but that I struggled to do so. So first off, this setup works with its local sensor plus up to 5 remote sensors and has the ability to hide sensor pages if they're not in use, as per your discretion. The buttons on the left and right allow you to move, well, left and right through the pages of sensor data. On each page of data, underneath the text readouts, there's a small auto-scaling line graph with its current range displayed as well. This graph shows the trend for that sensor over the past hour and automatically scales the Y range of the graph up and down if the differences in temperature are smaller or larger. And it also gives a range readout so you know what kind of a window you're looking at. Then, when the middle button is pressed, it opens up to a full-size version of these line graphs for a more in-depth look at the trend of the temperature for those that want it. And that's basically it. It's pretty darn simple, but honestly, that's what it should be. And it works quite reliably from my testing. Additionally, the temperatures are way more accurate, and if they are off, it's usually by less than a degree Celsius, and that's a small enough amount of error to reasonably remove it via an offset. And there's a place to do this in the code of the base station and of each of the remote sensors if you find that it's needed. So before I end this video, let's take a quick look at this new system versus the old system. Compared to the old remote sensor, the new sensor is actually a reasonable amount larger than the old one. But honestly, this isn't too bad of a thing. It helps the sensor not get dragged around as much by the USB cable, and it also allows for a more accurate temperature readout than before. Looking at the base station now, the overall form of it is quite different, and I think that the new buttons, and especially the new screen, make a massive difference. Even though the difference between the 2 screen sizes is technically only a ½ inch, the new screen feels so much bigger and is so much nicer to read. It can also display way more data, making these line graphs, honestly, possible at all. So hey, if you've made it this far, I highly recommend these SH1107 OLED displays for all kinds of projects. But yeah, that's this project wrapped up. I'm definitely glad that I revisited this, and I think that it came out really well. Even then though, there's still a lot of room for the system to get even cooler. Something I don't think I'll do, but that I would love to see someone in the community do, is add Home Assistant functionality to the base station, as it's got access to all of the data from the sensors, and it's got an ESP32 in it, with the idea of the built-in Wi-Fi being able to be used for this. Well, that's all that I have for you in today's video. I hope that you were able to at least enjoy it, and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.